today we're going to take a look at section 3.2. So in 3.1 we sort of developed the idea of what addition and subtraction means. That's what we did, okay? So we talked about different models for how we could ask questions or how questions could be posed that would require us to use addition or subtraction. What section 2 does is it actually tells us the how do we do it part. So these are called algorithms. So all algorithm means it is a process by which we do something. So you have an algorithm for what happens when you get out of bed in the morning until you arrive at class. It's the process by which you do something. And it doesn't necessarily have to be done always in the same order, but sometimes the order matters. For instance, it matters whether you put your underwear on before your pants on, right? But it may not matter whether you put your shirt on before your pants on. Okay, so there is a certain ordering to what's going on, but it doesn't always matter that it be done in a certain order. So what we're going to do is we're going to actually look at several different models for addition, and then we're going to do the same thing for subtraction. All right, so the first one is a concrete model. So the concrete model actually looks like we've got physical objects that we're working with. Okay, so I brought before to class what are called base 10 blocks. You guys remember those red blocks that I passed around that one day? Base 10 blocks are a concrete model. There's other concrete models. We could use money as a concrete model as well, and that would work very well for what we're using. I'm going to go with the base 10 block idea. Do you remember what the different objects look like? For instance, if I were to draw 34 with base 10 blocks, what would it look like? 3 what we call longs, and then 4 of the little bitty squares, right? The units. That's what we're going to do. So we're going to draw 3 longs. And just because we had them in red before, I'll fill them in red. Okay, that wasn't what I wanted to do. Let's try again. All right. So I'm supposed to have 3 longs. And 4 units. So this is 34. That's one set. And then we have the other set that's 18. And so what should 18 look like? 1 long and 8 units, right? Second set representing the number 18. And what we want to do is we want to combine these together. So this is the same kind of an idea as when you combine money. You would like to avoid as much change as possible. You like to change things into bigger pieces, right? So I don't want to carry around a whole bunch of dimes or quarters or something in my pocket. I'd like to turn them into dollar bills. Same thing here. So as you're taking a look at these, what items can you combine? The units, and how many units can be combined together? 10 of them. So if I take these 4 and 6 of these will combine into what? 1 long. Alright, so as I'm looking at combining these 2 sets together, how many longs will I end up with? 5 of them. And how many units will I end up with? 2 of them. So my concrete model, that is the tactile learners, the ones who like to touch things, you can actually physically move them around and you can combine them so that they actually work. And you end up with what value? 52. Any questions on the concrete model? So it doesn't have to be done with blocks, but that's one way to do it. Money is another excellent way to do this. We could have drawn dollar bills, and it would have worked fabulously. Dollar bills and what? Dimes. So if we had chose to use dollar bills, we want to use dimes for the next one. Or we can simply use dimes and we can use pennies, which would be fine too. The dollar bills is a little bit easier to work with simply because when you get so many dimes, you're going to turn into quarters, and we don't want to. That's not where we're headed. we're not really trying to change up money. So the dimes and the dollar bills work really nicely for this. Okay, let's take a look at another one. So that works, and it works just fine, but obviously if something gets too large, you really wouldn't want to be drawing concrete models for too long, right? But it has its place, especially for establishing the undercurrent of what's really happening. So as the numbers get larger, and I realize this is not large numbers, but I want to show you what it would look like with the same numbers, you have other methods available. So the next one we're going to look at is the expanded algorithm. Alright, so the expanded algorithm actually looks at each of the values in expanded form, which we've done before. Do you remember what 34 looks like in expanded form? Yes, so, and I'm going to take it one more step and actually write down this is 30 tens and 4 ones. Do you remember writing them that way? So we're breaking it apart by place value, and we're multiplying each value times its place value. So it's 3 times 10 because that's what the 3 in that location actually means. And then you can do the same thing with the 18. So how would I write that? 1 times 10 plus 8 times 1. And if you were really doing this sort of in a concrete way, like we did in the last one, you can add, but you can only add place values together. So we can start on the right-hand side, we can start on the left-hand side. It doesn't really matter where we start. We're just going to add straight down. So just to show you it doesn't matter, I'm going to go from left to right because a lot of our learners like to go from left to right. Any idea why they might do that? That's how we read, isn't it? So let's take a look. If I had 3 plus 1, I'd get 4. So I'd have 4 tens. And then I'd have 4 plus 8, which would give me 12 ones. And this is correct. It's just not sort of simplified, right? You wouldn't want to have 12 pennies in your pocket or 12 dimes in your pocket. You'd like to change them up into a smaller denomination of coin. So what we can do then is we can actually regroup. We can take this 12 right here, and we can regroup this as 2 ones and 1 10. So I've broken apart this piece into these 2 pieces. Right? That's what I did when I regrouped on the previous slide. But then I'm able to combine the 2 that are times 10s together. I have 4 10s and I have another 1 10, so it gives me a total of 5 10s plus the original 2 1s from the last step. And so my total is 52. Now, this is actually the model upon which our standard algorithm is built on. So the standard algorithm, that is the one that you know and love, that you learned way back when. Somebody lead me through, what do you do? We start on the right side. And what do we get when we add the 8 and 4 on the right side? We get 12. And that's where it a little bit deviates from this expanded notation, is that we really have to start on the right-hand side because we're sort of abbreviating the process of the previous model, okay, previous algorithm. So when we get 12, what do we do with the number 12? All right, so we write this 2 down right here, and we carry the 1. Why in the world did I carry a 1? Because that was actually the number 10. When I got 12, I got 10 and 2 1s. So I wrote the 2 1s down, and I carried the 1 for the number 10 over to the tens column. Then we add the 1, 3, and 1 together to get 5. So the standard algorithm combines the pieces that the expanded algorithm actually separated out. That's what it really does. Okay. All right, there's a couple other algorithms I want to show you. There's one that we're going to use some bigger numbers now. We're going to use the left to right algorithm because, just like we said a moment ago, students read from left to right, so sometimes this is a helpful thing for them to see that they have an option of. Now, there is a reason that this is the one that you learn, the standard algorithm. The reason, primarily, is because it's efficient. What does efficient mean? It's quick, right? I can do it very quickly. That doesn't always prove to be helpful in terms of understanding. So some of these other algorithms you're going to see are not going to be especially quick. But if the goal is to be able to understand it, we can get the quickness later. We want to understand it as well. So let me show you some others, but understand that they don't look as quick, and that's okay. All right, the next one we're going to do the left to right algorithm. I'm going to write it in that same sort of vertical pattern. So I put the 1, 5, 3, 4, and then underneath 3, 2, 1, 8. Okay, so it looks to start out just like the standard algorithm. We're writing on top of each other. And then what we do is we actually add up the first number in the left position. So we add 1 plus 3 and we get 4. And when we do that, we understood that 1 plus 3 was really 1,000 plus 3,000. So this is 4,000. So on the side, I'm going to write down what we added, just to remind you, not because you would really write it down if you were working the problem. Okay? That's where that 4,000 came from. So we did the first column. And then we do the second column. We have 5 plus 2, but that's really 500 and 200, which gives me a total of 700. And then I do the third column, the 3 plus the 1, which is really 30 plus 10, and 30 plus 10 is 40. And then I'm going to do, there's that 4 and the 8 that we had on the previous problem, 4 plus 8, which would give me 12. And 12 is really 12, so it goes in the ones place and in the tens place. And then we can add up the pieces that we got from our individual values, because nearly all of them end up being the only value in that column. Now, not all of them, but nearly all of them. So again, I can still move from left to right. I can write this as 4,700, but then I've got 4 plus 2. I got 5, so 52. It's not especially efficient, I get that. But it's very clear where all the numbers came from and why they got there. Ready for another one? Okay, lattice algorithm. The lattice algorithm will come up again when we do multiplication. At least in terms of multiplication, it is my daughter's absolute favorite way to do multiplication, the lattice algorithm. But it works for addition too, so we're going to start with it here. Okay, so it starts out looking very much like the last one did, right? 1894, 3218, and we're writing it out just in a vertical pattern, okay? What happens next is what's different. So underneath this, you're going to create a rectangular box, and you need to split the box into as many values as you're going to end up with place values for. So you're sort of splitting it up underneath the individual place values. Mine does not look evenly split, but there's going to be a 4-digit number when we get our answer. Okay, so you need a 4, well, and even, it's just because there's 4-digit numbers that you're adding. It doesn't mean because it's 4-digit numbers in your answers because you're adding it. Okay, so you draw 4 boxes all squished together underneath. So far, so good? Here's where the lattice comes in. You split each of the boxes diagonally. Each box is split. That's why it's called a lattice. So if you're familiar with what a lattice looks like, this has that sort of an image of what a lattice looks like. And you actually can add from left to right or right to left. It makes no difference at all. Okay? So if you want, you can add from left to right. I'm going to go from right to left on this one, just because the first was on the right-hand side shows mostly what's going on. If you get the 4 and the 8, you have 12. So with the number 12, the first digit goes in the upper corner, and the second digit goes in the lower corner. So a 2-digit number, the largest digit goes on the top, and the smallest digit goes in the bottom. 9 and 1 gives me 10. So again, the first digit goes on the top, the bottom digit goes on the right, or the other lower value goes on the right, bottom. 8 and 2 is 10, so we do the top and the bottom. Then the 3 and the 1 is the only case where we actually end up with it actually being a 1-digit number. We get 4. So if it's a 1-digit number, that goes in the ones place, which is the bottom corner. Okay, so what does this actually do? Well, what this actually does is it separates out the place value. So when you have the number 12 right here, you put the number 2 down here in the ones place, and this number 1 goes up in the tens place. Okay? So you're separating the place value for the second one. Again, the lower value goes in the ones place for that value, and the upper one goes in the tens place. Now, this isn't your answer, obviously, because I've got a bunch of numbers and I've still got it in this sort of a weird shape, right? So what is your answer? Well, your answer is what you get when you add your diagonals together. So we're going to take this diagonal, which is a 2. We're going to take the second diagonal, which is 1 plus 0, which is a 1. The third diagonal, again, 1 plus 0, which is 1. The fourth diagonal is 1 plus 4, which is 5. So you add them on the diagonal because what the diagonals did is they separated things out into its proper place value. And that one, at least, I don't think is really that much more work than the other method. It's a little bit more of a design going on. If your artistic kids will enjoy that, I don't know. But it really isn't a lot much more work. Let me make one comment upon this, though, so that you're aware. If you had numbers here, say like this that had 3 and this one was a 6, let's make it 8, 3 and 8. So if you had 3 plus 8, you would get what? 11. You'd put the 1 down and you'd have to carry the 1 to the next column. So there is some carrying, and that is a potential that could happen in the middle of this. It just carries to the next diagonal over. Yes,
Are we not adding two different place values? For like, because whenever you're adding a top and a bottom one, and it's a tens and a one.
This is a tens place from this addition, which was already in the ones place. This right here is in the tens place by very default of the fact that the 9 and the 1 were in the tens place to start with. So this is the tens place really right here, and this is actually the hundreds place. But when you think of them in terms of single digits, it's like the ones in the tens place. Yeah, good question. Okay, lattice algorithm. All right. Now all the algorithms we've done so far are really good for 2 numbers added together. I'm about to show you the scratch addition method, and scratch addition is helpful when you're adding a bunch of numbers together. Whether they're big or small, it doesn't matter, but you have those several. So think shopping trip at Walmart. You're trying to sort of add things up in the cart as you go. Estimate, exact, it doesn't really matter to me. But the issue is you've got a whole bunch of things that you're adding together. Good. So what I'm about to show you, really, the scratch addition would be utterly unhelpful if you were working with 2 numbers added together, the previous examples. Okay? All right, so here's 34, 18, 69, and 87. And the inherent problem with adding up a bunch of values together is that you have to keep counting some way. At some point, just knowing 5 plus 6 is 11 fails you because you end up with 22 plus 4. Well, I know that's really just 2 plus 4, but what you start doing is this. You start counting, you start using your hands. All right, so here's where this is cool. So we have 4 plus 8, and that's going to give me 12. I think this is about the 6th time we've done that one today, isn't it? Yep. Yeah, okay, 12. Well, what I'm going to do is I'm going to make a scratch, and I'm only going to remember the number 2. The number was 12. I'm ignoring the tens place. So anytime I get a number that's 10 or bigger, I scratch. And I only remember the ones value. So I'm only remembering the number 2 now. Now I've got 2 plus 9, which is 11. So I'm going to scratch, and I'm not going to remember the number 11. I'm going to remember the number 1, because it's the ones place of that digit. And then I have 1 plus 7, which is 8. And I write the 8 down because that did not exceed 10. Okay, the only time I scratch is when I exceed the number 9, really, when I got to 10 or bigger, 2-digit number. Yes, yeah.
What do you do with number 2?
Well, the number 2 is because there's 2 scratches, right? I scratched twice.
Well, 4 plus 8 is 12.
And I added that 2 to 9.
So you like to replace it?
Well, so let me write it out here like this. When I did 34 plus 18, 69, 87. What I really did when I scratched this is that I then considered that I only am working with the number 2. So now I'm adding 2 plus 9 to give me 11. So I scratch it and I write the number 1 down, or think about the number 1. So the 2 and that 1, they didn't go away, they just got added to the next value down the list.
Okay.
So I scratch to ignore the number in the tens place, and I only remember the number in the ones place. Now, I scratched it twice, didn't I? That is, I exceeded the number 10 2 different times. So each of my scratches is the equivalent of the number 10. I mean, that's what it was. I scratched so that I didn't have to remember the tens place. So that's 2 of them. I carry that over to the next column. So however many scratches you have, you can count them and carry it to the next column. Okay? We're going to try it again. So 2 plus 3 is 5, still a one-digit number. 5 plus 1 is 6, still a one-digit number. 6 plus 6 is 12. It's 12. So I'm going to scratch. Why did I scratch at 12? Because it's 10 or bigger, right? So I'm going to scratch to remind myself that I actually exceeded the number 10. But I'm going to remember the number 2. 2, because it was the ones digit of the number 12. 2. So then I have 2 plus 8, which is 10. And I'm going to scratch. But when I had the number 10 and I scratched, what's in the ones place? 0. So I'm going to write the number 0 down. How many scratches did I have? 2. So if you think about it, I'm really carrying it to the next column. There's nothing there right now, but that makes it easy, right? So I carry that up to 2, and I write down that I have 208. I use this all the time. It's the absolute craziest thing. And here's why. Because if we don't use something where we scratch, over here when I had 12, I have to do 12 plus 9. Right? I mean, that's 21, I get it, but I've exceeded the values in most standard addition, subtraction, flashcard sets once I get there. And even if I didn't then, when I got to here, I do, because now I'm at 21, and I have to have 21 plus 7. I don't have a flashcard for 21 plus 7. Again, I should be able to come up with the fact that that's 29, but that's not what usually happens. This is what usually happens. We start counting things out, all right? What this does is it eliminates having to do the counting. It reduces it all to the flashcards that you knew or learned, or the basic addition facts. So this is scratch addition. Scratch addition is helpful when I have what? Lots of numbers I'm adding together. Okay, I don't mean long values, I mean lots of values, individual values. So think about the shopping cart at Walmart. All right, so that's the addition models. So we're going to look at the subtraction models next. All right, so subtraction model is the concrete model. What's the concrete model for addition? It had the standard size blocks, right? We looked at those longs and the individual units. That's what's going to be for this one as well. So let's draw out 34. I already drew that, didn't I? My goodness, what in the world? All right, so I need 34. And I'm going to start by drawing that particular one. So here's 30. So we start with 34. And we're going to think about this very much like you did when you were writing up problems with the takeaway model. I have something and I'm removing part of it. So the concrete model is a really good picture for the takeaway description that we had. So I have 34 and I'm supposed to be removing 18, but there's a problem with that. What's the problem? Yeah, I don't have 8 units to take away. In essence, it says I'm supposed to take away 1 long and 8 units. Well, I can take away 1 long, that's no problem, but I don't have 8 units to take away. So what am I going to have to do? Take one of my longs and turn it into 10 units. Yeah, you guys are all saying it. Awesome. So sort of my next picture, and this is an equivalent picture, is it's going to be the same values that I have, but I'm not going to have 3 longs. I'm only going to have 2. And I'm not going to have 4 units, although I'm going to start out with 4. How many am I going to have? I should have the same 4 plus 10 more, so I should have 14. All right, so here's what I want. Okay, so I have only regrouped. I haven't actually taken anything away yet, right? But I'm about to. Now I can actually take away what I'm supposed to be removing, which is 1 long. So I can remove this one. He comes out. And what else gets removed? 8 units. Any of the 8 you like get removed. They're gone. And so your final answer should look like what? 1 long and 6 units. So my solution is the number 16. And we can concrete get our hands on that. We can feel that happening. I use the concrete model when I pay my children money, especially with my youngest, my son is 5. So he gets fined, my children both get fines for doing things that they shouldn't be doing. Okay? They get fined. They have chores that they earn money with, and they get fined when they misbehave. And so it is much more of an impact for him when I actually give him what he earned, and then he has to turn around and give it back to me because he had some sort of an error in his behavior. Okay, so we use this concrete model to reinforce that idea. It's something we use in our lives. All right. Starts to look like we're just doing everything all over again, doesn't it? We have the expanded model and standard model coming next. All right, so expanded model, you know how to write it now. How do I write 34 in the expanded model? All right, so 3 times 10 and 4 times 1. And then I'm supposed to be taking away 18. So this is actually taking away 1 times 10 and taking away 8 times 1. We're removing both pieces. So I'm sort of distributing that negative 3 because I want to make sure that we understand that I'm not going to do 4 plus 8. This is still 4 minus 8. But we've got a problem here, don't we? What's the problem? I can't take 8 away from 4. It's not a possibility. So what I have to do is I have to do some regrouping. I have to take this 3 and I have to change it into what? To 2 tens. And then instead of having 4 ones, I'm going to have 14 ones. And then I'm actually able to take away the 1 10 and the 8 ones. And again, you can move left to right or right to left once you have enough to remove things. So if you do 2 minus 1, you have 1 10. And if you do 14 minus 8, you have 6 ones. 1 10 and 6 ones, again, is the 16 from the previous slide.
So this one you should start from the right.
It doesn't matter. You can do either way. You can do it from the left. You just have to make sure that you've got your borrowing, your moving things right, your regrouping done before you start actually subtracting. So as long as you've got the regrouping done properly, it doesn't matter if you start from the left or the right. Okay. All right, so reminder of the standard model. What does it look like? What do you do? We do move from right to left. And in order for that to happen, what do you do, Karen?
Take away a 3 and add 10 to the 4.
Okay, so the 3 becomes a 2, and the 4 becomes a 14, and sometimes we abbreviate that and sort of just put the number 1 beside the 4. But literally, really what happened is that we turned the number 4 into 14. And we did that so that we can then subtract, right? So I can actually do 14 minus 8, which is 6, and 2 minus 1, which is 1. So it's just a compact way of doing the expanded model. That's all the standard model is. It's a compact or efficient way of doing the same subtraction that the expanded model did. All right, now we've got something different because you haven't seen this one, and it didn't have the counterparts for the other section. This is equal additions. Equal additions is the last one we do today. Equal additions is very interesting. We're going to write it just like the others. There is no borrowing. I want you to write that in big bold something on your paper. You do not borrow ever in equal additions. The whole point of equal additions is to avoid borrowing. Again, it may not be a method you like. I'm okay with that. But that's the point of the method. Equal addition says, if I add a value to the second one to avoid having to borrow, I think the number 2 would be nice. Why in the world do I like the number 2?
It's even.
Well, it is even, but what does it make? It's particularly nice. It makes a 10, right? It makes this 8 right here become a 0 at the end. That's my goal. My goal is to get a whole bunch of zeros as I do this. But if I add the number to the second value in my subtraction, I need to add it to the first one as well. I'm equally adding values to the first number and to the second number. Okay, 834 becomes 836, and 158 becomes 160. Thank you. Now, there's a problem here. If I stop here, I still have to borrow. Do you see it? Yeah, because I still have a 3 above a 6. So I am not done because I have not achieved my goal, that is avoid borrowing. So then what would I need to add to the second value to 40, right? Because if I just add 4, that becomes 164. That's not what I want. I want to add 40 because 160 and 160 and 40 is 200. But if I add 40 to the second number, I have to add it to the first number as well. This is still a subtraction problem. So what's 836 plus 40? 876. And what's 160 plus 40? 200. And now I can subtract and I do not have to borrow. Again, because I do not have to borrow, you could move from left to right or right to left at this point, couldn't you? What does this become? 676. Okay, equal additions. Okay, so we'll stop with equal additions and we will finish up the other methods when we come to class methods. Have a great couple days, guys.